Hello everyone, I am Hao Yang, a learning technologist at Udacity. I love to work with robots, whether it's a self-driving RC car, turtle bots, and drones. And I maintain courses here at Udacity.
Hello, I am Kareem, and I'm a content developer at Udacity. We work in the School of Autonomous Systems at Udacity, which in addition to the Robotics Software Engineer Nanodegree program, also includes our self-driving car and autonomous flight programs. We are here today to give you an overview of the program and walk you through the projects. We will also let you know why you should enroll and how this Nanodegree program will help your career as a robotics engineer.
For those of you who are new to Udacity, Udacity is a company founded by Sebastian Thrun. Sebastian, in many ways, is most well known as the father of self-driving car. Besides, he is the author of the book Probabilistic Robotics, which is one of the must-read books in robotics. He was a professor at Stanford and led the team to win the DARPA challenge. Then he joined Google and started the Google self-driving car program, now known as Waymo. He founded Udacity, aiming to bring education from Silicon Valley to the entire world, including robotics, self-driving cars, and flying cars. Now, let me give you a brief overview of our agenda. First, there will be the overview of the program. Then, we will discuss the career in robotics. And finally, there will be the projects and demo. Now, let's get started. Robotics is a subject focusing on robots. There are loads of different robots which are quite common nowadays. First thing comes to my mind about robots would be humanoid robots. They are quite prevalent in movies and literatures. Industrial robots or robotic arms are also robots, although they look more mechanical. Self-driving cars and UAVs are also robots, but they could sense their environment and adjust accordingly. Mobile robots, such as security robots, delivery robots, and vacuum robots are more and more popular in our daily life.
That's right. All items listed here, although very different in shape and function, is indeed a robot. Their behavior could be abstracted to three processes: perception, decision-making, and action. The robot first perceives the environment, then makes a decision about the next action, and finally execute the action. Whether it's a self-driving car navigating on the highway or a vacuum robot eating your socks, all of them follows this structure.
Currently, there are more and more robotic companies emerging and traditional industries starting to build robotics team, from warehouse robots companies, last mile delivery companies, to automotive companies and UAV companies. You might wonder what it takes to be a robotics engineer and work with robots. So, Kareem, what skills are needed to be a robotics engineer?
If you look for the demanded skills for robotics engineer, you will find that C++ is the most common language used in robotics industry. Also, proficiency in ROS is highly desired, since most of the prototyping is done on the ROS framework. Probabilistic robotics, such as localization, mapping and SLAM, navigation and path planning, is also required by employers to develop complicated robotics software. At Udacity, we work closely with leading industry employers to develop the right curriculum to support your career advancement. We believe there is no better way to understand exactly what skills top employers are looking for than to speak directly to those companies and professionals. Our new program focuses on teaching core, advanced, and transferable robotics skills, including probabilistic robotics algorithms with an intensified career focus.
Students will build a portfolio of 5 hands-on projects using ROS and C++, which is the most important programming language in robotics, to showcase to hiring managers and recruiters. Students will have a streamlined learning experience and utilize the in-classroom workspace to develop robotics software without needing to use a VM or purchase another Linux machine. So Kareem, let us explore what projects are there in the program.
Of course! Robot simulation is an essential tool in every roboticist's toolbox. A well-designed simulator makes it possible to rapidly test algorithms, design robots, perform regression testing, and train AI systems using realistic scenarios. In our program, you'll begin by prototyping robots in the Gazebo simulator. Gazebo offers the ability to accurately and efficiently simulate populations of robots in complex indoor and outdoor environments. You will begin by learning how to build new environments and deploy assets in Gazebo. In the Build My World project, you will work with Gazebo to simulate the inside and outside of a one-floor environment that will house your future robot. As you do so, you will gain proficiency with Gazebo and C++ plugins.
Awesome! Now we have our own simulation world. What's next?
In this second module, you will tackle the Robot Operating System, or ROS for short, beginning with an architectural overview of ROS. From there, you will learn about ROS workspace structure, essential command line utilities, and how to manage software packages within a project. Harnessing these skills will be key to building shippable software using ROS. Following this, you will explore ROS nodes, which are a key abstraction that allows a robot system to be built modularly. You will be writing nodes in C++ to control a robotic arm in Gazebo. In the Go Chase It project, you will use ROS to design and build a mobile robot. Then, you will house your new robot in the environment you built in your first project. Eventually, you will program your robot with C++ and ROS to chase a ball through this environment. As you work to successfully complete this project, you will acquire skills in ROS, Catkin workspaces, ROS packages, ROS nodes, ROS launch files, ROS integration, and C++.
So we have the robot up and running in the simulation world. Moving on to the third project. In this third module, you will learn to use probabilistic localization algorithms to estimate a robot's position and orientation. First, you will learn what it means to localize and gain an understanding of the challenges inherent to the process. Next, you will learn what a Kalman filter is and understand its importance in estimating noisy data. Inside the lab, you will implement an extended Kalman filter package with ROS to estimate the position of a robot. You will then learn the Monte Carlo localization algorithm to localize robots. Finally, you will code the MCL algorithm in C++. In the Where Am I project, you will develop an autonomous system to localize your robot. First, you will write a C++ node that will navigate your robot through a series of waypoints. Then, you will localize it with an AMCL package in ROS. Accomplishing this will involve gaining skills in localization algorithms, Kalman filters and MCL, ROS parameters, ROS packages integration, and C++.
Cool! We now know how to localize the robot. But how do we generate the map?
In the fourth module, you will study mapping algorithms. By combining mapping with the skills you learned in the previous 3 lessons, you will be able to implement simultaneous localization and mapping, commonly referred to by this acronym SLAM. You will first learn the occupancy grid mapping algorithm and code it with C++. Then, you will learn how to simultaneously map an environment and localize a robot relative to the map with the grid-based FastLAM algorithm. You will then apply what you've learned to interface a turtlebot with a grid-based FastLAM package with ROS to map an environment. Finally, you will learn how to simultaneously map an environment and localize a robot relative to the map using the GraphSlam algorithm. In the Map My World robot project, you will use an RTAP MapSlam package with ROS to simultaneously localize a robot and create 2D and 3D maps of your world. You will gain skills in mapping and SLAM algorithms, occupancy grid mapping, grid-based FastSlam, and GraphSlam, ROS debugging tools, and C++. I think now we are all set for the final project.
In this 5th module, you will learn how to search for a path and navigate it with classical, sample-based, and probabilistic algorithms. First, you will learn a number of classic path planning approaches that can be applied to low-dimensional robotic systems. Then, you will code the BFS and A-star algorithms in C++. Next, you will learn about sample-based and probabilistic path planning and how they can improve on the classic approach. In the home service robot project, you will integrate everything you've learned in this Nanodegree program to build a home service robot that will navigate to pick up and deliver objects inside a world of your own creation. You will gain skills in path planning, search algorithms, ROS navigation stack, and C++.
Now, let's move on to a coding demo in Udacity Workspace.
Alright, let's do it.
Hello everyone and welcome to today's Udacity Workspace coding demo. Udacity provides you with a in-classroom workspace, which is a remote Linux machine with ROS all set up, so that you could jump right into action and write robotics software code without the need to build a virtual machine or purchase a separate Linux laptop. I'm going to show that to you in this lab, right in ROS Nodes. This is part of the Robotics Software Engineer Nanodegree program, ROS Essentials. So in this lab, you will be required to code the control regime of this simplistic robotic arm. It has 2 degrees of freedom and the camera attached to the end of it. And you're required to input control values of the angles for this robotic arm, and also build a function which will redirect the robotic arm to be looking at those 3 interesting cubes, whenever it detects the camera is actually looking at something boring, for example, uniform image. Okay, now let's move over to the Udacity workspace and see it in action. You could generally find the workspace in the very beginning or at the end of a lesson, and here you could locate it here in the ROS in the Udacity workspace concept. And it will prompt you to enable the GPU mode. You would need it because you would need to use the remote desktop come with it. So I'm going to enable it and give it some time to load, and now we are already in the Udacity workspace. Let me expand this, look better. So on the left you have a file explorer. You can see the path here is in home workspace, and you have a simple file editor here. You could open up a file and do your edit here. And down there, there's the terminal. It is the same as a Linux terminal. You could do lists, you could check the environment variables, and you can see all the variables are all set. It's ready to go. Okay, now with GPU enabled, we could go to the remote desktop, and it will provide you with a full Linux experience. Now let me pull up the terminal here, and this is exactly the same environment as I just show you here. Okay, so I have already cloned the source code to the Catkin workspace here. Let me show you what are there in the source folder. So as you can see, we have the arm mover, the look away, and simple mover source file. They are all implemented already, which will send control signals to the robotic arm. I'm going to do a quick build, and it compiled successfully. Now don't forget to source the setup script. And now we're ready to launch a simulation. I'm going to do a ROS launch simple arm. The launch file I'm going to use will be robot spawn.launch. It will spawn the environment as well as the simple robotic arm to the environment. Now let's give Gazebo a moment to load. Okay, so it's already there. As you can see, it is pointing to the 3 cubes on the desk. Cool. I think it would really help us if we could see what image the camera is actually capturing. Let me pull up another terminal and launch the RQT image view. And the topic we want to subscribe to be the image raw. Okay, so now we have the actual image shown here. As you can see, this is actually the image captured by the camera attached to the end of this robotic arm. Cool. So now let us move this robotic arm. How do we do that? I'm going to use the raw service call here. Okay, we need another terminal here. Let me place it down here. We need to source the subscript as well. And then I'm going to call the service of the arm mover we previously coded. We're actually going to use the safe move. And the parameter used to be, let's give joint 1 some rotation, and joint 2, let's do 0 as well. Let's see how the robotic arm perform. Okay, it's looking at the seating, and oh no, that's a uniform image. So it sent a message to move it back to the original position, looking at the 3 cubes. And now we can try something else. Let's start from this. Let's try 90 degrees. Okay, so it's looking at something not that much interesting, but still it's kind of boring. But I mean, it's not a uniform image, so that the move to center function will not be called. And again, let us move it to the top seating, and it's moving back again. So this is the simple arm lab in action in the Udacity workspace. Okay, now that's a wrap for the demo of Udacity workspace. Remember that all these are happening right in your browser. You don't need to set up anything else in order to use it. You just need your browser. And the environment is already configured for you so that there's no apt-get install ROS and configure the keys, etc. You can jump right in and start coding in this classroom workspace. This wraps up our deep dive into the Robotics Software Engineer Nanodegree program. Now, we are excited to answer your questions live during our Q&A. Cool. So thanks again for coming in today and learn more about the Robotics Software Engineer Nanodegree program. So I'm here for a Q&A, and I'll start with a few questions that comes in when we first released the program. So first, who is this program for? So I would say if you are already in the software engineering industry, and you have experience in software engineering and want to learn more about robotics and how to build robotic software application, this program is perfect for you. You will leverage your skills and apply them to build your own robots and robot softwares. And also, if you are a maker and you are already familiar with the hardware such as Raspberry Pi, a BeagleBone, or Arduino, this program will give you a good start to build and unleash the full potential of your hardware, because you could incorporate ROS and all the ROS packages other contributors created into your own applications. And thirdly, I would say if you are very interested in probabilistic robotics, this course is for you. You will learn more about how the founder of Udacity, Sebastian Thuren, wrote and built all the probabilistic robotics algorithms from localization to SLAM and to path planning, and you could have a better grasp of all those knowledge. So let me rewind to the prerequisites of this course. So you have a programming experience, and most preferably C++, and you should have math skills as calculus, linear algebra, probability. They're all kind of required in this program. So if you are interested in pursuing a career in autonomous systems, this program is for you. So the next question I have here is, what kind of service do I get as part of this Nanodegree? This is really a great question. So if you are already a Udacity alumni or veteran, so you are already familiar with the mentors, the reviewers, and the community we provided. So on top of that, I would really want to mention that in this program in particular, you have the classroom workspace, which is a really powerful tool for you to start coding robotics software without the need to purchase any separate Linux laptop or set up a really huge virtual machine on your computer. And also, we have recently launched all series of career services, including GitHub profile reviews and LinkedIn profile reviews, and also will help you to build your resume using all the projects and applications you built throughout the program. This is really beneficial because although you have all the knowledge equipped, it is not there until you've shown it to all the potential employers. So this would be a huge plus. And also we have a specially created a autonomous systems interview course for you to handle all the common questions and some tips and tricks you need to succeed in the autonomous systems related, robotics software related, and even software and hardware related field to master those interviews. So these are all the services you'll get throughout the program, and I'm really looking forward for you to join. So the next question I have here is, why is this program C++ only? So just bear with me if you are already familiar with C++, but I would like to give 3 points on this question. So the first one is, your robotic software really need to run in real time, and you want your code to be fast. C++ is a compiled language, and compared to Python, it does not need to be interpreted on the fly. So this gives it a huge advantage when building those real-time applications. And secondly, with C++, you can navigate all the ROS packages very easily. To give a somewhat off analogy, I would say using C++ for robotics is kind of like using JavaScript for front-end development and maybe use Scala for big data applications. It's very nice of you to have C++ equipped so that you will have a much wider options when building your own software programs. And finally, I think C++ really has an advantage when it comes to hardware, because device drivers, those low-level control interfaces, are usually written in compiled language such as C and C++. And with an understanding of C++, it will be really helpful for you to better understand how each component of the system works, and you have a better grasp of all your robot applications when developing those. Cool. So on top of that, I would like to mention that if you want to learn more about the building blocks of C++, you should check out the C++ Nanodegree program that Udacity develops, where the creator of C++, Bjarne Stroustrup, will lead you through the basics and advanced topics of C++. Cool. Now let me get to the live questions today. I got the first one from Carlos. Carlos was asking about, do you need a virtual machine for this course? So I think I just covered that a bit, but you don't. So you don't need to set up a full Linux image on your computer because it's already there in your classroom. It's in the Udacity workspace. It's a full-size Linux machine where it's the exactly working environment you will be working in when you are developing on actual robots in Linux space. So just navigate to your classroom, as I've demoed in the previous demo, and boom, it's all there, it's all set up, and you could start coding your robotics software application right away. So I got another question from Rohit. So do you need to be an expert in C++ to take this program? I would say no, because in fact, if you are coming from a compiled language background, or you are already familiar with something like Java, I think you are already in a good position, because although ROS provides a lot of specific packages, you will have a better grasp of all the underlying concepts of ROS, and could just jump in faster. But if you are coming from JavaScript or Python, then I would suggest you to check out more about C++ first, so that you have a better understanding of how those nodes, how those software components are talking to each other, and you have in a better position to understand the hardware related and just integrate it closely with all those software. And another question from Tassin. Do you make 3D SLAM, or it was only align visualization? So in the program, we covered occupancy grid mapping, grid-based FastSLAM, and also the graph SLAM. And in the actual project, you will be using the R-type mapping algorithm developed by Matthew LeBay, which Udacity had an interview with him exclusively. Sorry. So it actually requires you to create both a 2D and a 3D mapping of your own environment in the simulation. So that will be a very cool project. So next question is from Sarah. In the robotics field, how common possible are remote employment opportunities in the US? For this question, I would say first, traditionally, robotics is really has a lot of focus on hardware, because you kind of need to integrate all the software you built to an actual actual hardware. So that would be mostly preferred on site. But recently, there are a lot of cloud robotic services coming up. Most notably, last year, Amazon launched their AWS RoboMaker, which allows you to develop all robotic software applications on the cloud and from simulation to deployment. So I would say there will be more and more opportunities in developing robotic software remotely, because the big data platform, the cloud computing platform are growing and growing. It's like a major development area for all applications, I believe robotics included. And another question is from Sriram. Is there any hardware material in this course? Do we work with a physical robot? So in this course, as the name suggests, we will be mostly focusing on software engineering on ROS, and we'll be mostly completing the projects in simulation. I would say simulation will be the very much starting point of all robotics software development, because you don't really want to just bash your robot, $5,000 robot, into a wall and have it all broken. So simulation will give you a solid understanding and starting point from developing more complicated robot applications. Okay, so next question from Noman. Those will be the last questions today, and I'll be answering the questions in the later part. Do you have an algorithm that teaches AI to make robots smart? So I would say that is a good question. So for ROS, for this program, you will be mostly dealing with ROS packages. And in the self-driving car algorithm program, you do have a chance to apply sensor fusion and comment filters and all those advanced skills, deep learning, computer vision, to build a self-driving car, which would be the most hot area, the hottest area these days in the autonomous systems. Yeah, so that's all I have today. I'll get to the questions later. Okay, so all right, thank you very much.